Okay, so much of what we're going to be doing today is based on this oxidation chart. So I hope that you have a copy of that and put it off to the side because we're going to constantly refer to it. So I hope you do have that. Okay, first thing I want to consider with you is a couple old sayings. Saying number one is you can't get blood from a turnip. I've never been sure exactly what that means, but I guess the idea is a turnip doesn't have any blood, so it's impossible to do that. An old saying number two is you can't get honey from a stone. Again, there's no honey in a stone, so it sounds impossible. Now here's a new chemical saying. You can't get electricity from a lemon. Okay, let's see if that's true or not. Now, to try to get electricity from lemon, here's what you would need. You need a lemon, and you need a penny and a nickel. Now, I want you to look at the chart, the electromotive chart. It turns out that metals don't really like to be in their pure form. The copper of a penny would rather be copper ions, and it has to shoot off electrons to do that. Well, this situation here gives them a chance to do that. Same thing, nickel metal would rather be nickel ions. That's its more stable state. But to do that, it has to shoot off electrons. So it's a fight between penny and nickel as trying to shoot off their electrons. Now, rather than look at a picture of this, I'd like to see if I can actually do this for you. I happen to have, this is my favorite part of the course, by the way, because I get to do open heart surgery on a lemon. So I'm going to make 2 incisions. Okay, and I happen to have a nickel. So I'll shove a nickel in here. And I happen to have a penny. So I'll shove a penny in here. And I want you to observe the voltmeter. Okay, I hope it's visible to you. And by the way, I'd appreciate some oohing and awing from you guys. That would be helpful. There we go. Okay, we just lit up New York City. Okay. Now, again, we're not really getting a heck of a lot of electricity yet. The thing that's amazing is you get electricity at all. Okay, well, this is going to be the kind of the basis of our lab today is to find out how can we get electricity. And so this is the introduction to electrochemistry. Now, it turns out the lemon battery is kind of hard to analyze because of the organic chemistry of the lemon. So we're now going to go to a simpler cell to analyze. That would be the zinc copper cell, or zinc copper battery. Okay, so notice we have 2 beakers. One contains zinc sulfate, the other copper sulfate. And it's very typical in these cells that a metal is sitting in contact with its own ions. So zinc metal, contact with zinc ions.
Professor Berg.
Contact with copper ions.
Professor?
Negative ions are really not too terribly important. Okay, so you're looking at the zinc copper battery. And what we're going to do is we're going to go through these 7 leading questions. And by going through these leading questions, you'll really analyze the cell. Okay, now the first one is actually the most important of all, direction of electron flow, because if you can figure that out, then, are you seeing it? Okay, if you can figure that out, it kind of leads to the other questions. Now, what you have to do is look on your half reaction chart and realize it's a competition between zinc and copper. They both want to push off electrons. Who's the better electron pusher? So I'm looking at the chart also. So it looks like zinc is about a quarter of the way through, and copper is way down there. Copper is about 4 below hydrogen. So would you agree that zinc is a better electron pusher? Okay, so you're looking at those 2 blue arrows, and what they tell you is, yes, zinc is the one that yippee gets to push the electrons through the wire. Okay, next leading question is, let's look at the half reactions. Now, what you want to do is you want to pick the half reaction that goes along with the electron flow. In other words, if zinc is the winner, that means underneath the zinc cell, you show the zinc pushing off the electrons. So here's the zinc metal, and it's going to produce zinc ions. Okay, so that half reaction agrees with the electron flow. Now, if copper is the loser, that means that it's going to pick up electrons. Okay, so the electrons are going to go on the surface of the copper metal, and then what's attracted negative positive? So the copper ions are going to migrate over, and they're going to pick up those electrons. Okay, so copper plus 2 is going to react with 2 electrons to produce copper metal. So that's the second leading question, is to get the half reactions. Okay, now you guys know how to add half reactions together. So below that, you'll see the overall reaction. Now notice I nicely picked two half reactions that have 2 electrons each, so they cancel out. So the reactants are zinc metal. It's going to react with copper ions to give you copper metal and copper ions. Now, there's something else that the overall reaction tells you, and that is that zinc metal would love to pass electrons directly to copper plus 2 ions, but it can't do that because they're in separate compartments. The zinc metal is on the left, and the copper ions are on the right compartment. So we've kind of tricked nature. In other words, they like to pass electrons directly, okay, but we've stopped them by doing that and putting them into separate compartments. By the way, that's one thing that goes wrong sometimes with the battery, because if the copper ions somehow come in contact with the zinc metal, the electrons will be passed directly and not through the wire. And that's what goes wrong with your car battery sometimes, is the solutions get together. They're not supposed to. They're supposed to be separated, and they kind of get together. Okay, so what have we gone through? So we've got electron flow. That's leading question number 1. The half reactions, that leading question number 2. Okay, the overall reaction, that's leading question number 3. Next question is that the compartments are labeled cathode and anode. Now look at the box down here, and it gives you, based on first principles, the definitions of cathode and anode. So the anode is the compartment where oxidation is occurring. So look at the zinc half reaction. Zinc 0 is going to zinc plus 2. It's definitely being oxidized, and so that compartment is called the anode. By the way, sometimes they call the zinc metal the anode itself instead of just a reaction. Now, the definition of the cathode is the half reaction where reduction is taking place, and sure enough, the copper 2 is going to copper 0. It's being reduced. Okay. Now, how is a student to keep this straight? One thing is you can use the alphabet. Notice that O and A are both vowels, so put the vowels together, oxidation and anode. And notice R and C are both consonants, so put the consonants together, and you can do it that way. I remember there used to be a commercial many years ago for this cola called RC Cola, and they'd show this girl dancing around holding some RC Cola, and she'd say, "Me and my RC." So RC, reduction cathode. So whatever works for you, that's a good thing to do. Okay. Now, the next leading question is we're going to get mathematical. We're going to calculate the cell voltage. So what you want to do is take the 2 half reactions again. So here's the zinc half reaction and the copper half reaction, and you want to line them up so you can get the overall reaction. Now what you want to do is you want to use your chart to look up the voltage of these half reactions. So the zinc going to zinc plus 2 has a voltage of plus 0.763 volts. Now notice the copper half reaction is the reverse of what's on the chart. So look on the chart and you'll see the copper half reaction is about 4 under hydrogen, and it says negative 0.337 volts. How come Berg reversed the sign and made it positive? Because if you switch the half reaction around, you have to switch the sign. Okay. So now you algebraically add them together and you get a voltage of plus 1.10 volts. Couple comments. First of all, that is a very small voltage. 1 volt? I mean, you guys have 9-volt batteries that run your radio and stuff like that. I'll explain later how this can be magnified. Okay, but that is the voltage of the cell. Now, do you see that positive number? This is very important. That positive number means we've done everything correct so far. The positive means this is a spontaneous reaction, and every single arrow is in the proper direction. Now, I want to go back to picture number 2. Do you notice I have the 2 beakers separate from each other? Now let's pretend for a moment, instead of this being a chemistry class, this is an invention class. And let's say that I set this up and want to show you that I get some electricity. It turns out there's something wrong with this setup. Nature would only allow about 3 electrons to flow and then it would stop. Anyone see what's wrong with this setup? I'll give you a hint. It has something to do with the ions. See, the problem with this setup is that if the electrons flow into the right-hand compartment, then you're going to deplete the copper ions. You're going to lose positives and you'll have too many negatives. They won't be equal. Same thing on the left-hand compartment. Okay, if you produce some extra zinc ions, there'll be too many positives. So therefore, this is not going to work. So let me go back to the system that actually does work. Notice in this one, I push the two beakers together, and let's pretend like I drilled holes in them so we can have what's called ion flow. So that's the next leading question, is ion flow. Now, pretend like instead of holes, this is a porous material. For example, clay works very well. Okay, clay has holes small enough so the ions will not flow on their own, but big enough they'll flow if they have to. Okay, so let's follow the ion flow. Okay, so if electrons are flowing to the right-hand side, the copper metal has a negative charge on it. Okay, that means that all the positive ions are going to flow towards it. So notice I have an arrow from copper +2 going to the right-hand side. Notice the zinc +2 also flows to the right. Okay. Now, on the left-hand side, if electrons are leaving the zinc, that means it's going to have a positive charge to it. Okay, so what's going to be flowing over there? The negative sulfurs are going to flow in that direction over to that side there. And the ions are very clever. They move at such a rate so that if you have any one part of the solution, in that solution, overall the charge will be neutral. By the way, that's actually an interesting thing you'll study in advanced class. It's called ion mobility. You actually will calculate how fast the ions move. But they're very clever. They move at such a rate, so overall you'll have overall neutrality. And it's got to be that way, or you won't get electricity. Nature won't stand for it. You have to have overall neutral. Okay, so I think we've named everything now except for the last question, which is positive negative posts. Okay, now this is kind of confusing for this reason. Okay, you see the positive charge on the zinc and the negative charge on the copper. That's what the ions see, but it's not what you would feel if you were to grab onto these posts. So look at this little man in the top here. The reason a light bulb is lighting up is because if he grabs onto the zinc piece of metal, it will feed electrons into his body. Okay, so for that reason, we label the zinc as a negative post and the copper as labeled as a positive post. So again, these are labeled top and bottom. Those like quotes about them. That's how the posts are labeled because that tells you where the electrons are coming from. So this is very valuable. For example, let's say you have this giant cell. You have some kind of battery or cell, and you can't see the chemistry inside of it. Okay, the way it's labeled, that tells you where the electrons are coming from. Okay, since the zinc is giving off the electrons, it's labeled a negative post. Again, don't get confused on what the ions see and what you would feel. Now, to test this out after class, I want you to go into your garage, lift the hood up your car, and I want you to grab onto the negative post of your battery. And sure enough, you'll feel electrons being given off. Just kidding, don't do that. But anyway, that's the way this is labeled. Okay, I would now like to give you a few moments to answer the leading questions for this particular cell. Okay, so there's the 7 leading questions. Okay, and this is going to be the ever popular cobalt cadmium battery, or say cadmium cell. So notice you have cobalt metal in contact with cobalt chloride and cadmium in contact with cadmium sulfate. So I'm going to give you about 3 or 4 minutes to see if you can answer these 7 leading questions on this particular cell. Or the key one would be the direction of electron flow. If you can get that one correctly, you can probably get the rest of them. And again, you'll need your half reaction chart to see who's the better pusher, cobalt or cadmium. Okay, Berg, stop talking. We want to work it on our own, so why don't you see what you can do. Okay, so let's discuss this now. Okay, so first of all, question number 1 is flow of electrons. Okay, so I look on the half reaction chart. It's a fight between cadmium and cobalt, and cadmium is a little bit better pusher than cobalt. So notice I have the electrons leaving the cadmium and going to the cobalt. Okay, so that's leading question number 1. Okay, so leading question number 2 is what are the half reactions that take place then? Okay, so you want to have the half reactions consistent with what is happening. So if cadmium is shooting off the electrons, notice the cadmium half reaction shows electrons being produced.